Bismillahirrahmanirrahim. Assalamu alaikum dear students. I am Arif and I welcome you all to lecture number 21 on the subject of computer organization and assembly language programming. Well, the title of today's session is Hack Assembly Programming Part 3. Well, this is a continuation of previous two sessions in which we wrote a Hello World hack assembly program and executed it in the hack CPU emulator. We discussed the concepts of program termination, built-in symbols, labels, variables, branching, and iterations. We also reviewed different hack assembly programs and executed them on the CPU emulator as a proof of these concepts. Well, dear students, today we are going to finish the hack assembly programming part. We will talk about how we handle something called pointers and how they are helpful in manipulating arrays. We will write programs that manipulate our input and output devices. We will see how we can do debugging inside our CPU emulator. So we have a lot to do today. Let's start playing. And let us begin with pointers and arrays. And let me straight away move on to an example in which pointers come into play. Well, consider this a very simple piece of code that many of you have written in your programming fundamental course. Well, there is a for loop that runs n number of times and initializes first n entries of this array named ARR with the value of -1. Well, you can assume that this is an integer type of array and is declared somewhere above this piece of code. So this is a C-like code, very easy to understand and very easy to write. But how to write the same logic in assembly language, the hack assembly language? Dear students, you really have to work much harder to deliver this required functionality. Well, before we do that, here are some observations that I want to share with you. Well, variables that store memory addresses like ARR in this example are called pointers. Abstraction of arrays exists only in high-level languages. In machine language, there is no abstraction of arrays. Rather, array is a segment of memory of which we know the base address and the length of the array that the programmer has declared. Arrays are implemented as a block of memory registers, and in order to access these memory registers one after the other, we need a variable that holds the current address. So there is nothing special about pointer variables except that their values are interpreted as addresses. Suppose this is our data memory or RAM. And just to remind you from previous lecture that in hack assembly the variables are allocated to RAM from addresses 16 onward. And each variable is a 16-bit value and there is no type associated with a variable. So let's fall back to this and let us first initialize these three variables ARR to 20, N to 5 and I to 0. And let us start by writing the hack assembly for this line of code. So first we place a constant inside the D register by using the A instruction and then using the C instruction. Now we create a variable named ARR. We know that a variable is a named memory location, and in hack assembly variables are allocated to RAM from address 16 onward. And since this is the first variable, so you can see in this illustration that this name ARR is associated with RAM address 16. Let me repeat it again. The moment I have created this variable ARR over here using this syntax, this name is associated with RAM address 16. The next task is that we need to write the value 20 inside this variable at RAM address 16, and this can be achieved using the C instruction. Okay, so we are done with the high level language code. ARR is equal to 20. We have written the 4 corresponding hack assembly instructions which perform this task. Now let us write hack assembly for n is equal to 5. So first we place the constant 5 inside the D register. Now we create a variable n, you see over here as well, since this is a second variable. So you can see in this illustration the name n is associated with RAM address 17. The next task is to write 5 inside this memory location, inside this variable n, and this is achieved by m is equal to d, a C instruction. Finally, now let us write assembly for I is equal to 0. We simply create a third variable named I associated with the RAM address 18, and to initialize it with 0 we have this simple C instruction, m is equal to 0, that will do the job. Dear students, before we review the actual loop code on the next slide, let me say a word about these 3 variables. N is a variable that contains a value 5, and this is the maximum number of times this loop should execute. I is the loop variable or the counter variable initialized to 0. Each time this loop iterates, the value of I is incremented and the loop breaks when I becomes equal to n or I becomes equal to 5. Finally, this variable ARR is initialized with a value of 20, and this is not a data value, rather is the starting address of array ARR. So this arrow describes the pointer variable. So ARR sub 0 will map to address 20, ARR sub 1 will map to address 21, ARR sub 2 will map to address 22, and so on. Now this slide shows the continuation of code from the previous slide. Here the actual processing will be done. This is the label named loop, and at the bottom here is an unconditional jump back to this label loop. And within these 2 instructions, we need to write assembly code to initialize the RAM addresses 20, 21, 22, 23, 24 with a value of -1. Or in simple words, need to initialize the 5 slots of this array ARR with a value of -1. Okay, the first thing that we do is we translate the termination condition for this loop into its corresponding assembly, and the termination condition is if I double equals n, then we need to go to end. So here at the bottom we have created the label end, and following this label we have the 2 program termination instructions. Okay, coming back over here. Well, dear students, these 6 hack assembly instructions are going to check if I double equals n, then go to end. And this is done by subtracting I and n, and after subtraction, if d becomes 0, d semicolon JEQ, this instruction will move the flow of control to the end of the program. Okay, so now dear students, we just need to write the task which the loop needs to perform, and that is to initialize the array or RAM address pointed to by ARR with -1, and then we need to increment the loop variable I. So these five summary instructions perform the initialization. They are self-explanatory. If you have gone through the previous lectures of hack assembly instructions, and these two instructions perform the increment. And this brings me to the end of this program. This snapshot shows the contents of this RAM after the first iteration. Note the RAM address 20 is now initialized with a value of -1, and this I has been incremented and contains 1. This is the snapshot after the second iteration. Two locations have been initialized, and after the third iteration, and so on. Okay, so now I think the code is quite clear to you all. Let's have our demo of this program on the CPU emulator. Our CPU emulator is already running. Let us load this program from lecture codes, lecture number 21, and the name of the program is arrays.asm. So this is the program. Well, review the code. Note that all the labels and variables have been resolved by the emulator. And let us run this program by clicking this button. Remember, dear students, RAM 16 this is ARR, RAM 17 is N, and RAM 18 is I, and they are all initialized. And the array elements to be initialized are from location 20 onward. So now 20 has been initialized with 1. You can see after some time location 21 will also be initialized. Let me increase the speed a little bit of this simulation. So you see all the registers changing their values, and after we are done with the initialization of all the 5 locations of this array, the code will come up over here in the program termination loop. And there you go. Well, my dear students, I strongly recommend that in your own time you should execute this program by single stepping. Keep noting down the contents of different registers and RAM locations, and verify your working of each iteration with the output produced by this emulator. Let me stop the execution of this program and fall back to slides. After having seen as to how pointers and arrays work in assembly, now is the time to see the code that interacts with the screen and the keyboard, the output and the input devices. Well, dear students, we have already talked about interfacing of the screen and the keyboard with our hack computer in lecture number 18. So here is the screen chip on our CPU emulator. This is a simulated screen with 256 columns and 512 rows. And here is the simulated keyboard. We have talked about this in detail in the previous sessions. Okay. So remember, this screen is having its pixels. If a pixel is 1, that means it is black. If it is 0, that means it is white. And this screen is memory mapped onto RAM addresses from 16384 to 24575. Similarly, this keyboard is also memory mapped, and it is memory mapped to the address 24576. Okay, so it is shown over here as well. And here is the memory mapping. This is the overall hack RAM chip. This is RAM chip of 32K words, and the initial 16K words up till addresses 16383 are for data or general purpose usage. Then we have the screen memory map of 8K words, and you can see the base address of this screen memory map is 16384. Then we have the keyboard memory map, which is just a 16-bit register at the address 24576. Well, whenever we want to write this screen, we write in the screen memory map, and in the next refresh cycle, the contents are displayed on the screen. Similarly, whenever we want to read the key pressed by the user on the keyboard, we will simply read the 16-bit word at memory address 24576, which will be the ASCII encoding of the character pressed by the user on this keyboard. And this slide shows the mapping of 131072 pixels of this screen with the 131072 bits inside the memory map. My dear students, in lecture number 19 we have discussed in detail as to how a 2D address of a pixel on this screen, that is a row and a column, is mapped onto a specific bit inside the specific word of this screen memory map. If you are not clear about this, I will strongly recommend that you should go through lecture number 19 of this course. And this slide shows you how to handle the keyboard. Well, very simple. When the user presses a key, for example, over here the key K is pressed, you can see its ASCII is there inside the RAM address 24576. The ASCII of K in decimal is 75, and this is the binary equivalent of 75. Okay, dear students, let us do a bit of graphic designing using hack assembly language. Well, this is a screenshot of our CPU emulator. This is the assembly code inside the ROM, which is capable of drawing a filled rectangle at the upper left corner of this screen. The width of this rectangle is 16 pixel, while the height of this rectangle is specified by a number written inside RAM address 0, which is 50 right now. So this filled rectangle is 16 pixels wide and 50 pixels long. Now the question is, how can we write such a program? Well, it's simple. We just need to run a loop 50 times, and in each iteration of the loop we need to write 16 ones at specific word inside the screen memory map corresponding to these 16 pixels of 0th row, then first row, then second row, then third row, and finally 49th row of this screen. Let's talk about the pseudocode for this program. So this is the pseudocode. The loop is running, let's suppose n is 50 times, and each time we are going to write 16 ones, 16 binary ones at appropriate locations over here. So we have the variable addr, which points to the starting address of the screen memory map, that is 16384. This is a built-in constant, built-in symbol. We have a variable n that is initialized with the RAM contents at address 0, not shown over here. I am assuming that the contents of RAM at address 0 are 50, so n is initialized with 50. So this is the number of times the loop will iterate. This is the variable I, the loop variable, which is initialized with 0 and will be incremented with each loop iteration. Okay, so this is the program termination instruction, and the actual code will come in between this loop and go to loop. And this is what we need to do to draw the rectangle. We need to write 16 ones. This -1 means 16 ones because this is in 2's complement. We need to write 16 ones at the first word of the zeroth row, the first word of the zeroth row. Then we will need to move down to the second row, then the third row, then the fourth row. And we have seen before that if we want to move on to the second row, we need to add 32 to this address. So we will keep adding 32 to the address, which will move us to the next row, and this process will repeat until the loop breaks, that is the I becomes equal to n. And this slide shows the hack assembly program corresponding to the pseudocode discussed on the previous slide. I leave it as an exercise to you. Review this code and understand it. And let me show you the demo of this program on the CPU emulator. Let me move over here. It is already running. Let me clear the contents of the RAM. Let me load the program. And this time the program is rectangle. So this is the program. Let us write RAM 0 with a value of 50 and run it with lesser speed so that we can understand it a little bit. Okay, so the program has started its execution. You can observe the first 16 pixel of zeroth row, and of course they are mapped to the RAM addresses 16384. So first the RAM address 16384 will be written with -1, and in the next refresh cycle you will see a line over here. Let's wait a bit. 16384, the starting address of the screen memory map. It will just turn up over here. Oops, it is not turning up. I hope I have loaded the right code. Okay, so actually this 50 has not been entered. Actually to enter this 50 I need to press an enter. Now it has been entered. Let me rewind this and let me rerun it again. I'm sorry for that. So once again we need to wait till the program writes a -1 at RAM location 16384. So this is the address 16384 and we have written a -1 and you can see a dash over here. The next address will be +32, that will 16448. Now the RAM location 16448 will be written with -1 and you will see another line in the next row, you see, and the third row will correspond to the address 16480. Let us wait for 16480. Once the RAM address 16480 will be written with a -1 or all ones, this will become more thicker. 16480, you see, it has become more thicker. So let me make it more fast. And you can see the rectangle is growing quickly now. I hope this concept is clear to you. And after we are done with drawing a rectangle of the required size, the program has entered inside the program termination loop. Let me stop the execution of the program and falls back to the slides. Okay, now let's see another program, an interactive program that receives input from the user via keyboard and act accordingly. This is a screenshot of the CPU emulator. The code is not completely visible to you. The complete code of the program is uploaded in the course Bitbucket repository. A portion of it is visible over here. Well, dear students, before you execute this program in the CPU emulator, please select no animation from this drop down, and this program actually listens to the keyboard. That is, it continuously read RAM address 24576, and if the contents of the RAM address 24576 is 0, that means no key is pressed, so this screen stays white. That is, all the bits of this screen memory map are written with zeros, and when any key, I repeat, any key is pressed, all the bits of the screen memory map are written with ones, so the screen becomes black. So this is the concept of the program which is behaving with the input of the user via keyboard. So let me again move on to the CPU emulator and see this program in action. Let's clear the RAM again. Load this program. The name of the program is fill.asm. Remember, these programs are already uploaded. Okay, so we need to select no animation from this drop down. Now let me run this program. So this time you don't see the instruction inside the ROM being highlighted as they execute, but in the bottom left of the CPU emulator you can see the message that the program is running. Okay, now let me press a key. So I have pressed the key N. You can see the keyboard has gone black. Let me raise my finger from the key. The screen has gone white. Let me press a Q. Let me raise it. Let me press a key. Let me raise my finger. Let me press a key. Let me raise the finger. So that is great. That is great. Let's stop the execution of this program and fall back to slides again. Well, dear students, before I close today's session, let me tell you that many of the times your programs might not run as expected or might not produce the correct results. It is then that this debugging jumps in to help you out. To me, debugging is the science and art of finding and eliminating bugs in a computer program. You have already observed that our CPU emulator continuously keeps track of all the registers and RAM locations. Other than that, it allows us to apply breakpoints and watch points. A breakpoint actually stops the execution of a program when the execution reaches at a specific line of code, while a watch point is set on a variable. And when during the execution of the program the value of the variable change or matches a specific value, the program execution pauses. Well, this slide shows the snapshot of our CPU emulator. Let's suppose some program is loaded over here, and if you want to put a breakpoint, you click this flag type of button. This opens up the breakpoint panel. Right now it shows that the previously declared breakpoints, 3 previously declared breakpoints are there. You can click this plus minus and this tick button to add, delete or update breakpoints respectively. Well, if you click this plus button, another window will open. In the right drop down over here, you can select one of the 6 options, the A register, D registers, program counter, and the time, maybe RAM or ROM. And over here you can select the address of the RAM, because the RAM is selected over here. So I have selected RAM address 21. You can place or specify a value over here at which you want to stop the execution of the program. And once you select this button, you see a new breakpoint has been added over here. And after doing that, you simply run the program. The emulator will pause the program execution when either this A register becomes 2 or this RAM address 20 becomes 5, or if 12 time cycles have elapsed or this RAM 21 becomes 200. Well, dear students, this is a very powerful debugging tool. Do make use of it. And this slide shows the overall development process. We write down the assembly program using our favorite text editor. We load that program into the CPU emulator and run it. If we are happy with the results, enjoy. If not, then find and fix the errors. And this slide shows the best practices that I expect you to follow while doing hack assembly programming. Okay, so that is it, dear students. I hope today's session was informative for you all. If you have liked it, please subscribe my YouTube channel and share it with your friends. I wish you all the best, happy learning, and Allah Hafiz.